Hello and welcome to another video with your favorite educator, Stephen Mendes. Calculating power factor correction. Now this is a very intriguing problem and we're just going to go through this problem quickly, but it's very relevant to the electrical engineer or the budding student of electrical engineering. And we have a simple factory with some motors. Most factories have several different motors to move their conveyor belts and control their machinery. And each motor can be represented as an inductor with a resistor in series. So here we have 3 of those motors. And our job is to put a capacitor across the power lines so as to bring the power factor to unity, which in actual fact, in simple terms, is actually making the circuit resonant so that the current will be in phase with the voltage. So if you don't understand all this, you need to go and do some background. This video is not for everybody, but this is presuming some sort of knowledge of phasors and the AC behavior of these circuits. So we have to try and make the current in phase with the voltage, because when we do that, we make the operation very efficient and less electricity is used, less heating in the wires, and your power bill is in a good standing. So we actually pay the electrical engineer because we save on the power. So if you want to go that route, you can make some money. Now, take a look. We have each of the motors classified as a complex impedance, Z1, Z2, and Z3. First, we must compute the combined impedance of Z1, Z2, and Z3. And here might be a good idea to go and watch my video on complex numbers. If you've ever not seen it before, you can go and look at it now and quickly get a feel for what we're trying to do. Basically, we're using the formula for resistors in parallel, which is 1 over R1 plus 1 over R2 plus 1 over R3 equal to 1 over RT. But when it's applied to impedances, each of those is a complex number or a reciprocal of a complex number, as shown. Now, the formula that we use for the complex part, or the imaginary part of the complex number, is simply omega L, which is the inductance, and omega is 2 pi F. So basically, we've come up with those complex numbers there by simply putting the resistance as the real part and the inductance multiplied by 2 pi F. Remember, F is 50 hertz, so it's actually 2 times 50, which is just 100 pi, times the inductance, and that gives us those complex numbers. After we take the reciprocal of them, add it together, and then take the reciprocal of that, we end up with, of course, a complex number, A plus JB. And the A and the B have those long, nasty numbers there. And the only reason why I've included all those decimal places is those students who love to play with calculators will be able to make sure they've done it right if they get that real exact number. But in actual fact, to come up with an answer in electronics, you never really go to all those long decimal places. But bear that in mind, because we're now going to manipulate A and B and simply plug the real value in at the end of our computation. Okay, so in order to get unity and to get rid of all reactance in the circuit, so that the main current will be in phase with the voltage, we have constructed an equation there. Now, this equation is just your good old equation for 2 parallel resistors. R1 times R2 over R1 plus R2, which you're probably very familiar with, except now that we are using the impedances. So we have Z1 times Z2 over Z1 plus Z2. Now in this case, the first Z is the equivalent impedance of all our motors, which we just worked out, A plus JB. And the second Z now is simply the capacitor, so it has a 0 real part And the capacitive reactance is obviously 1 over 2 pi Fc, the capacitance. So we have our omega there, 1 over omega c, as the reactance, and it's negative because of the reality of the phasors. When we put them into the complex form, the reactance comes out positive and the capacitance comes out negative. Now, we've made that equal to y plus j0 because we really don't care what y is at all. We're not interested in y. We just want to get the imaginary part of the complex number to be 0, because then it will mean that the reactance is 0. We will have a totally real circuit and our voltage and current will be in phase. Okay, so now we do some fancy maths. You can look it through, and if you have any questions, you can put them down in the comments. But basically, we're just pushing the algebra around. We're realizing the denominator, which is the big job that we're doing here. We're realizing the denominator, as I've indicated there. And after we've done that, we can ignore the real denominator and concentrate on the real part. Concentrate on the imaginary part of the numerator, which we want to be 0. So there we've picked out the imaginary part from the previous expression that on the previous page that we had, and we've made it to 0. So those terms relate to the imaginary part, which we've equated to 0 there. And once again, we do some fancy algebra on them to make C the subject, because C is the only unknown entity. And as you can see, once we've done that, we come down there, we solve for C in terms of A, B, and the omega. And lo and behold, out pops our capacitance, 48.5 microfarads, and we're done. See how easy that was? And thanks for watching this Stephen Mendes video, and we'll see you soon again in the next video.